Okay, there's quite a bit going on in this question. We've got to use distributional approximations. So we're going to be setting up some exact distributions and then approximations to them. And there are two different claims being made. Okay, so the first thing to do is to do your underlining really carefully in the question. What I'm going to do is just focus on one claim at a time. So the first claim is that one of these models has an 80% chance of covering that many miles without a major breakdown. Okay. Then there's another claim. I'm going to skip past that. But the data for this first claim, the researcher tested a sample of 113 cars covering 40,000 miles. So that is about this claim, about the 40,000 miles, and found that 17 of them had a major breakdown. So the first claim is about major breakdowns within the first 40,000 miles. Okay, we have 113 cars, fixed number of cars. There's a claim that each one has an 80% chance of breaking down, and I'm counting how many do. So I'm counting the number of breakdowns amongst these 113 cars. So this is at least claimed to be a binomial distribution. So for part A, the first claim, we're using a binomial distribution. We know there are 113 cars, and it is claimed that the breakdown rate is 80%, 0.8. So this is the distribution that the claim is being made holds. So I can go to my hypotheses. Remember, for a binomial test, okay, H0 is a statement about what P is, and H1 is a statement about either a one-sided or a two-sided statement about P. So the claimed value of P is 0.8. Now I have to test whether this is a directional claim or not. So the manufacturers, it can be helpful to actually say which of the two hypotheses is the manufacturer's claim. So the manufacturer's claim is this, and they're claiming it equals 0.8. They're not claiming it's at least 0.8 or at most 0.8, so therefore any evidence is anything other than 0.8 is going to be evidence to reject H0. So I have a two-tailed alternative hypothesis. Now if I were doing this as an exact test, I would take the observed values, which is 17 cars broke down, and I'd work out either the probability of being less than or equal to 17 or greater than or equal to 17 using the binomial distribution. Whichever of those was less than half, I'm not bothered which side it is because it's a two-tailed test, but one of those, whichever of the two was less than a half, I'd go with. But I'm not doing that. I'm doing an approximation. I'm turning this into a z-test. So I need to go from my exact distribution to my approximate distribution. Okay, now there are actually two approximations, you know, for binomial, but this one has got a p-value that's not particularly close to 0 or 1. It's got to have a large n, otherwise I can't approximate it, but it's going to be a normal approximation. Okay, if this was a very small value here, you could consider a Poisson approximation. Okay, but this is going to be a normal approximation, so I need a mu and I need a sigma squared. Now if you've got the original versions of these notes, you've got to be really careful. Can you make sure that in this table you've corrected these? Obviously these are variance formulas and they've misprinted as being for standard deviation. So mu and sigma squared, so the mean of a binomial is np, and I've got an n into p, so it's 113 times 0.8. And the variance of a binomial is np brackets 1 minus p, which is 113 times 0.8 times 0.2. So we work out both of those things, and the mean is 90.4, and the variance is 18.08, but I'm going to be using sigma, so it's a good idea to write down sigma, which is the square root of 18.08. Okay, so I have got my hypotheses. I'm now ready to get my test statistic. So my test statistic is a z statistic, and z is x minus mu over sigma. Okay. Now for a normal approximation to a binomial, if you were working out probabilities, you'd do a continuity correction. But they let you off on hypothesis tests. They say if you don't do your continuity correction, you'll get away with it. So if you do the wrong continuity correction, it'll be wrong. So we're never going to do the continuity correction. Okay, we're just going to go straight ahead, take the observed value of 17 as our x. If you see on a mark scheme 16.5 or 17.5, it'll be the version where they have done the continuity correction, but 17 is correct. 17 will be marked right. Minus mu. So the mean is, something's gone wrong. I can see immediately that 17, the observed value, is hugely far away from the mean. So I must have done something wrong. So 17 of the cars had a major breakdown. But the 80% chance is the chance of not having a major breakdown. So my observed value is not 17. Okay, 17 cars do have a major breakdown, so the cars without a breakdown is the other ones. And there were 113 altogether, so it's 113 minus 17, which is 96, is my observed value. So my Z formula, I do 96 minus the mean of 90.4 divided by 18.08 square rooted. That's going to give me a Z value. Here we go, 1.317. And that's my test statistic. So I'm ready to do critical values. For critical values, we always have a picture. Okay, this is Z test. We draw normal. It's two-tailed, so I need that tail and that tail. The significance level is 2.5%, which means the total probability shaded here and here must be 0.025. So the size of each individual tail must be a probability of 0.0125 here. That's half of 2.5%, and the other 0.0125 here. Okay, so I can find, using my calculator, this Z and this Z is 0 in the middle, so I'm going to have a negative Z and a positive Z. Okay, now both of them are critical values, all right? The calculator likes the probability to the left, so it's actually this Z, the negative Z, that's easier to find. So if I go into my normal inverse mode, which is option 3 on your distributions menu, 3, there we go. Okay, my area, I'm going to enter the 0.0125 as my area, and I'm expecting a negative Z, and indeed I get a minus 2.241. So this Z here is minus 2.241, this is plus 2.241, and this unshaded bit in the middle, we label that not significant. So where am I? I've got a Z value of plus 1.317. Now that's less than this. So it's there. I'm now moving on to my comparison. Let's just state my critical values before I move on. So my critical values, there were 2 of them. It was plus or minus 2.241. All right. My comparison, I've already started to think about my comparison. My comparison, I said that my 1.317 is less than 2.241. It's actually greater than minus 2.241. Okay, which is obvious because it's positive. Okay, but the upshot of this is this is the bit that you'll get marks for, comparing with the other positive critical value. That's enough to show me that this is not significant. So I write not significant. I say that we are going to be, therefore, if it's not significant, we are accepting H0, and that's the end of the comparison. We've just got to do the conclusion in context. I'm running out of space. Okay, but because we're accepting H0, because it's not significant, there is insufficient evidence or no evidence. You'll get away with no evidence. It's shorter, so that's what I write. There is no evidence. It's nice to say at the 2.5% level. Okay, okay, and now I've got to decide. I've got to maybe go back to the wording of the question. But a good question to ask yourself is, are you concluding in favour of the claim or against the claim? Now, the manufacturer's claim was that it was 80%, which was H0, and I'm accepting H0. So therefore, I'm going to be saying something that is generally supporting the manufacturer's claim, but it's a no evidence situation. So I can't say there's evidence the claim is true, so I have to say there's no evidence at this level that the manufacturer's claim is false. Okay. Now, at this point, I do need to make sure I've fully addressed the context, and there were 2 claims going on. So I could say there is no evidence at the 2.5% level that the first claim by the manufacturer was false, but I could say the actual details of the claim. So there we go. So there's no evidence at 2.5% level that the claim that 80% of the cars don't have a major breakdown in 40,000 miles, there's no evidence that claim is false. We are supporting the claim, That's as much as we can say in support of the claim. We haven't proved it's true, but we've tested it, and there's no evidence that it's not true. So we have loads of negatives in there. Okay, we have no evidence that it's false, and the claim was about not having a major breakdown. So loads of nots in that sentence, but that will get you the marks. Okay, moving on to the second claim. Okay, so let's do some different underlining. The second claim is that major breakdowns for this model have a constant average rate less than 2 breakdowns per 100,000 miles. Okay, so I'm looking now at the average number, the rate of breakdowns per 100,000 miles. So I'm counting breakdowns in a fixed space of miles. So this is going to be a Poisson distribution. Let's find the rest of the information about this claim. So what else haven't I underlined already? Altogether, the cars would cover 7 million miles with 109 major breakdowns. Oh, so we've got 7 million miles here instead of 40,000, instead of 100,000. So if there's a rate of 2 per 100,000 miles, that suggests a Poisson distribution. But the actual data I've got relates to a different number of miles. Okay, so let's actually examine these Poisson distributions. Okay, so the first Poisson distribution, so for the here where you can see me. Okay, so for the first Poisson distribution, when I'm talking about 100,000 miles, the claim is that I've got a Poisson distribution and there's an average of less than 2 breakdowns per that 100,000 miles. Okay, but we've got a situation with 7 million miles, which is 70 times as many. Okay, so for 7 million miles, I'd have to scale up the mean by 70 times, so 2 times 70 is 140. And this is, the claim is that this mean actually shouldn't be 140, it should be less than 140. So we have a Poisson-based situation. We can state our hypotheses. Okay, for our Poisson test, okay, the null hypothesis is always a fixed value of lambda, and H1 is going to be another statement about lambda. Okay, so in here, in this one, the fixed value of lambda I've got is 140. Okay, it was originally 2, but the data I've got is for 7 million miles, so I have to use 140. So I have to convert the manufacturer's claim. Okay, look at that. The manufacturer's claim is that the average rate was less than 2 per 100,000 miles. In other words, that it is less than 140 for the 7 million miles. So this is now going to be a one-tailed test, but this is the manufacturer's claim. So unlike the previous example, the manufacturers are not only making a one-sided claim, but it's the claim that I'm using as my alternative. Okay, so that will become important when we come to interpret at the end. And so it's one-tailed. All right, so I've got my exact distribution, it's Poisson, but the injunction, the instruction to use a distributional approximation is still in force. So this is a large lambda, so it's okay to set up a normal distribution. So my approximate distribution is normal. I need a mu and a sigma squared, and of course for the Poisson distribution, mu is the same value as lambda because that's the mean, and the variance is always the same. But I want to know that sigma squared there. Let's not get it wrong. I want the sigma. So sigma squared is 140. I have to square root that for sigma, which is what I'm going to need for the next bit. I've done hypotheses. I'm now going to do my test statistic. So my test statistic is going to be a z, and z is x minus mu over sigma. Okay, so I know my mu is 140, I know my sigma is the square root of 140, and the observed value, go back to the question, okay, it turned out that there were 109 breakdowns in the 7 million miles. So I need to put in, what was that, 109, so I need to put 109 in here, I need to calculate this z. Once again, I'm going to be able to get away with AQA without doing the continuity correction. So if you ever see 0.5s going on here, it's because they're doing it, but we don't have to. So 109 minus 140 over root 140 is a z of minus 2.61, or minus 2.62, minus 2.620, rounded correctly. Okay, so I've got a test statistic, great. Critical values. one-tailed test. The claim is about being the alternate is low values. So it's this bottom tail. I'm only going to be impressed by negative z's, which is what I've got anyway. That will usually happen. So this critical region, I'm sticking with a 2.5%, I think, significance level. Yes, there it is. We've used 2.5% significance level. So this is an area this time. It is 0.025. One-tailed, so I don't have to split it this time. So in my distribution mode, once again, I need to go into inverse normal. So that's 3, and I need to enter 0.025, and I'm expecting a negative z. Do I get a negative z? Yes, I do. It's minus 1.960, minus 1.960, and there is my diagram for my critical value. I need to state critical value equals minus 1.960. Next step is the comparison. So my comparison, well, minus 2.620 is here. It's less than minus 1.960. It's a bigger number on the face of it, but it's more negative, so it's in here. This white bit, of course, is my not significant bit. So I can see that this minus 2.620 has made it into the critical region. So this is significant, and so therefore I'm going to be rejecting H0. Right, so that leads directly into the first word of my conclusion. Because I have rejected H0, because it is significant, it means there is evidence. So the conclusion begins to write itself. Okay. So there is evidence of what? Okay, well, there's evidence that makes me reject H0, so I'm going to be going with H1. And H1 this time is the manufacturer's claim. Okay, so although I'm rejecting H0, previous example, H0 was the manufacturer's claim. Now I'm going with the manufacturer's claim. But now I'm saying I've got evidence. So this time I'm going to say there's evidence the manufacturer's claim is true. Okay, when we're finding in favour of H1, we're actually saying something very positive. We've got evidence it's true. So I could just say there is evidence the manufacturer's second claim is true. You might get the marks for this, because there's a bit of context. I'm referring to a claim, okay, but I should say second claim, but you're safest to say what that claim was. So the claim was that the average number of major breakdowns in every 100,000 miles is less than 2. So I said that. I've confirmed that there is evidence the claim is true. I've done my conclusion in context. So that all that remains on this question is to answer B, which we've kind of done as we've gone along. We've got to explain why the approximations we used were justified. So for the binomial one, okay, n was, I've still got it here, 113, which is large, and p is 0.8, which is not close to 0 or 1. By close to 0 or 1, we mean very close to 0 or 1. So even 0.1 isn't that close to 0. Might even get away with a normal approximation with 0.1, 0.02 close to 0. And then for your Poisson one, the second one, for the second approximation, we had a lambda. Now there were two values of lambda, remember. Okay, for the 10,000 miles that we originally had to consider, it was 2, but for the data we actually had, we had to use a Poisson with lambda of 140. That's the relevant one. So lambda equals 140, which is large. So I've done it in note form here, but I've made the essential points. The binomial distribution could validly be approximated by a normal because n was large and p was not close to 0 or 1. And the Poisson distribution I used could also be validly approximated by a normal because lambda was large. And now I'm done.